Okay, in order to talk about addition rules for probability, we have to have a common definition. We talked about this a little bit earlier this year, but let's talk about it in this context. That is mutually exclusive events. In order to understand what a mutually exclusive event is and how it works with probability, we need to have a definition. Okay, and I just went ahead and took the definition from the book. Two events are mutually exclusive if they cannot occur at the same time, meaning no outcomes are in common. So for example, what happens when you flip a coin is mutually exclusive from what happens when you roll a die. Okay? They don't impact each other, they don't affect one another, they are mutually exclusive. What happens to the coin flipping does not affect what happens to the die tossing. So we're just going to get right into it. You can take a picture of this if you want. We're going to go through these 4 different scenarios and decide whether or not these events are mutually exclusive or not. The key thing here is that the 2 sort of events that are happening are we're rolling 1 die for each event. Okay. Really what you're trying to determine in terms of whether or not these things are mutually exclusive is if both of the things can happen at the same time. If both of the things can happen at the same time, then they are not mutually exclusive. If they can't happen at the same time, they are mutually exclusive. And notice here, they're all divided up with the and. So on the other side of that red slash that I put there, those are the 2 events. That's what splits the 2 events up. So go through and decide, if you can, which ones are mutually exclusive and which ones aren't, and then we'll come back and talk about it. Now, after you've come up with something, turn to somebody near you, discuss, see what you came up with. Which ones are mutually exclusive?
The first and last.
The first one and the last one, that is correct. Okay, so you can't, if you roll an odd number, there's no way to roll an odd number if we're trying to figure out getting an even number. Those are completely separate from each other. Getting a 3 and getting an odd, well, 3 is already odd. So those are contained in both. So we throw that one out. Getting an odd and getting a number less than 4, how many ways can you get an odd less than 4? 2. So you can get a roll 1 or a 3. Getting a number greater than 4, so 5 or 6. Getting a number less than 4, 1, 2, or 3. Those are completely separate. There's no overlap. Make sense? Mutually exclusive. There's no overlap there. There's no outcomes in the same pile, so to speak. Okay, so let's talk about the addition rule. When we have 2 events, A and B, and in all those situations that I gave you, the left side of the slash was sort of like A, the right side of the slash was B. Okay? When you have a situation where those 2 events are mutually exclusive, the probability that A or B will occur is the probability of the first event plus the probability of the second event. That's all that means. Okay? So if we went through and looked at those situations before, we could use this rule for the first scenario and for the last scenario because those were the only 2 that were mutually exclusive. So the second rule is, let's say A and B are not mutually exclusive. We can still find the probability. The trick is, and this again goes back to that example we talked about last week, you just have to subtract one of them off. So when they are not mutually exclusive, you have to subtract off when A and B both happen. Because it gets counted in A, it gets counted in B, so we don't want to count it more than once. Okay, so that black 5 we talked about last week. If we were looking at the probability of getting I think it was black 7. Probability of getting a 7, or the probability of getting a black card. Okay, the problem is there are black 7s, so you have to subtract off the ones where they both happen at the same time, because otherwise you'd count them both in event A and event B. So when you're working on these problems, you have to decide, okay, are these mutually exclusive or not? And if they are, then you can just straight add, come on, you can just add the probability of each one if they're mutually exclusive. If they're not mutually exclusive, you have to subtract off the probability of both of them happening, because they're already counted in A and B. So if I subtract one of them off, then I'm going to be good and I won't have counted too many. So here is, speaking of Krispy Kreme, we're going to talk about donuts. This is on page 200 if you'd rather screenshot it from your book, or you can take a picture of the screen. So I want you to try to work through this. I'm not going to coach you through it yet. I want you to give it a shot and see what you come up with, okay? And then we'll come back together and find out if your thinking was on target or not. And let's just get something out of the way right now. I understand that oftentimes math problems are not very realistic, okay? The fact that you would walk into a donut shop and close your eyes and randomly choose a donut, like, that's not going to happen. I understand that. I'm not going to try to convince you that people do this. But it applies for our situation, and it allows us to go through the mechanics of finding probability. So let's just clear the air on that one right now. Okay, first question. Are the events that we're talking about mutually exclusive or not? Can you get a glazed chocolate donut at this particular donut shop? At this donut shop, can you get a glazed chocolate donut? That's how they would both happen at the same time. The answer is no. You can't. You can get glazed, you can get jelly, and you can get chocolate. Those are your only options at this particular donut shop. You can't get a glazed chocolate for this problem. Okay? It may be unfortunate, but you can't get it. Okay? So, in this case, so once we've determined that these are mutually exclusive events, all you have to do is find the probability of selecting a glazed donut and the probability of selecting a chocolate donut and add them together. Okay? So here's what this problem really is. The probability of glazed or chocolate, and because they are mutually exclusive, because we can't get both at one time and make that one donut at this shop, okay, we can just add the probability of glazed plus the probability of chocolate. How many did that? Okay, so what's the probability of getting a glazed donut?
8, 3, 1/2.
How many are there total? How many donut possibilities are there?
1, 4, 3.
Listen to my question. How many donut possibilities are there altogether? 12. How many ways can you get glazed? 3. So that's going to be 3 out of 12. Chocolate is just 5 out of 12. You add those together, and oftentimes, so one of the things that you'll find is it makes more sense most of the time to wait to the end to reduce. Okay? Because I already will have a common denominator in that case. 8/12 reduces to what? 2/3. Okay. So the probability of getting a glazed or a chocolate is 2 out of 3. Okay. The other way you could have looked at it is you could have just added to begin with 3 plus 5, 8/12. Same thing. How many had 2/3? Okay, good. Any questions about it?
Why did you do over a fraction? Like in fractions?
That's probability is pretty much always in fractions. Every once in a while you'll see it as a percent or a decimal, but most of the time it's a fraction.
Wait, that's the answer?
That's the answer, 2/3. 2/3 of the time you'll get a glazed or a chocolate. Okay, let's look at another one. This one is on page 201. Go ahead and try that one out. Are these mutually exclusive events? Why not? So some can be black and an ace. Okay, so how many of those are there? How many black aces are there? There's ace of spades, ace of clubs. So there's two situations where both can happen. Okay? So you have to take that into consideration. These are not mutually exclusive, which means you're going to have to subtract those ones off when you're calculating this. So let's talk about this situation, okay? Again, we're talking about the probability of an ace or a black card. So in theory, what we do is we say the probability of getting an ace plus the probability of getting a black card. The problem is, because we just already discussed this, you can get black aces. You have to subtract them off. Now let's understand why you subtract one of them off, okay? Okay, so I'm going to have to subtract off the probability of getting a black ace of when they both happen. See, because here, just from a numbers perspective, there's 4 aces, okay? So I'm counting 2 of those black aces here. In the black cards, there's 26. And I'm also counting 2 of those black aces over here, which means I've counted them in both probabilities, which means I have too many of them. So instead of counting 2 of those black aces, I subtract 1 off to balance that out. Okay? When they're not mutually exclusive, that means when they both happen at the same time, they're being counted here and also here. That's why we have to subtract one of them off, because we've counted them too many times, and we'd end up getting a probability we'd actually get a probability that would be too high. Okay? So the probability of getting an ace is what? 4 out of 52, a black card. 26 out of 52. And black aces, we already determined there were 2 of those, so 2 out of 52. So this is what my setup looks like. And I would, rather than trying to go through it all in your head and cancel them out and all that stuff, I would stick with this, subtracting the probability of them both happening at the same time. Because eventually we're going to get into some probabilities where there's 3 events and 4 events instead of just 2, and they're going to get more complicated. And keeping it all straight is going to be tricky. So again, these are the ace and the black card, and then we subtract off when they both happen. So of course this is 28 over 52, reduces to 7 out of 13. Okay? Are there any questions?
That made a lot more sense.